Hold on to your hats, space explorers, because our solar system might be a lot more crowded than we thought. Recent discoveries suggest there could be dozens, maybe even hundreds of planets lurking in the cosmic shadows. That's right, not just the familiar 8 or 9 we learned about in school, we're talking about a whole bunch of celestial objects vying for the title of planet. This begs the question, what exactly defines a planet in the year 2024? It's a question that has astronomers buzzing like excited neutrinos because the answer, it turns out, is far from simple. The very definition of a planet is a moving target, constantly evolving as our understanding of the universe expands. What was once a straightforward concept, a large, round object orbiting a star, has become a cosmic conundrum with implications for how we view our place in the cosmos. Buckle up, because we're about to embark on a thrilling journey through the ever-changing landscape of planetary science to uncover the truth about these celestial wanderers. Defining a planet might seem as easy as identifying a tree. It's big, it's round, it orbits a star, right? Not so fast. Over the centuries, our definition of a planet has been as changeable as the tides. Early astronomers, armed with nothing more than their eyes and a thirst for knowledge, classified anything that moved across the sky as planets, including the moon and the sun. It wasn't until the Renaissance that we began to understand the true nature of our solar system. Then came the discovery of Uranus and Neptune, followed by Ceres and Pluto in the outer reaches. Suddenly the solar system felt a bit more crowded. But were these new objects planets or something else entirely? The debate raged on with no clear consensus. It became clear that we needed a more precise definition, a set of rules to separate the planetary wheat from the cosmic chaff. Enter the International Astronomical Union, IAU, the official governing body for all things space. In 2006, they decided to settle the planet debate once and for all. They established 3 criteria that an object must meet to be classified as a planet. First, it must orbit the sun. Second, it must be massive enough for its own gravity to pull it into a spherical shape. And third, it must have cleared its neighborhood of other objects in its orbit. This last criterion proved to be the most controversial, as it effectively demoted Pluto to dwarf planet status. Pluto, it seemed, hadn't quite tidied up its cosmic backyard. While the IAU's definition brought some order to the chaos, it wasn't without its critics. Some argued that it was too restrictive, potentially excluding objects that might otherwise qualify as planets based on other characteristics. Little did we know, the universe had a few more surprises in store. Let's start with the seemingly straightforward criterion of roundness. The IAU states that a planet must be massive enough for its own gravity to pull it into a spherical shape. Makes sense, right? Planets are round like basketballs, while asteroids are often lumpy and irregular. But here's the catch. Even smaller objects like dwarf planets can be round. Take Ceres, the largest object in the asteroid belt. It's a fraction of the size of our moon, yet gravity has molded it into a perfect sphere. So, where do we draw the line? How round is round enough? The IAU's definition doesn't offer a precise measurement, leaving some wiggle room for interpretation. It's like saying a planet needs to be big enough without specifying how big that actually is. And what about objects that are almost but not quite spherical? Are they forever relegated to the cosmic minor leagues, denied planetary status despite their best efforts to conform? The question of roundness, it seems, is more complicated than meets the eye. Now let's consider the role of gravity, that invisible force that shapes the cosmos. The IAU tells us a planet's gravity must be strong enough to dominate its orbital neighborhood. Essentially, it needs to be the biggest fish in its pond, gravitationally speaking, but gravity is a fickle mistress. It's not just about the mass of the object itself, but also the influence of nearby celestial bodies. A planet orbiting close to its star, for example, might have a harder time clearing its neighborhood due to the star's powerful gravitational pull. Imagine a cosmic tug-of-war, with planets vying for dominance in a complex gravitational dance. It's not always clear who the winner will be, and a slight shift in mass or distance could tip the scales. The IAU's definition, while well-intentioned, doesn't fully account for these intricate gravitational interactions. It's like trying to define a dance competition based solely on the size of the dancers, without considering their rhythm, technique, or the music itself. Perhaps the most contentious criterion for planethood is the idea of clearing the neighborhood. According to the IAU, a planet must be the gravitational bully on its block, having either absorbed or ejected any other objects in its orbital path. This criterion has been particularly troublesome for Pluto. Its orbit is littered with icy bodies and other remnants from the early solar system, leading to its demotion to dwarf planet status. But Pluto isn't alone in its cosmic clutter. Even Earth shares its orbital neighborhood with a few thousand asteroids, remnants from the solar system's formation. Does this mean Earth is in danger of losing its planetary card? The IAU argues that the size and gravitational dominance of Earth far outweigh these minor orbital companions. But it raises the question, how much cleaning is enough? Is it a matter of quantity? Or is there a certain threshold of orbital tidiness that a planet must achieve? The case of the exoplanets. The IAU's definition, while perhaps adequate for our solar system, faces its greatest challenge when we look beyond our cosmic backyard. The discovery of thousands of exoplanets, planets orbiting other stars, has thrown a wrench into our neat planetary classification system. Many of these exoplanets are unlike anything we've ever seen before. Hot Jupiters, gas giants orbiting scorchingly close to their stars, defy our understanding of planetary formation. Mini-Neptunes, smaller versions of our ice giants, blur the lines between gas giants and rocky planets. And then, there are the super-Earths, rocky planets larger than Earth but smaller than Neptune. These enigmatic worlds challenge our assumptions about planetary composition and the potential for life beyond our solar system. The IAU's definition, based on observations within our own solar system, struggles to accommodate the sheer diversity and strangeness of these distant worlds. It's like trying to fit a square peg into a round hole, forcing a one-size-fits-all definition onto a universe that delights in variety. As we delve deeper into the cosmos, discovering new and ever-stranger worlds, the IAU's definition of a planet feels increasingly inadequate. It's becoming clear that a simple three-point checklist may not be enough to capture the complexity and diversity of planetary systems. Some astronomers propose a more fluid definition, one that takes into account a wider range of factors, such as an object's composition, formation history, and even its potential for hosting life. Others argue for a more nuanced approach, recognizing different classes of planets based on their unique characteristics. The debate over what constitutes a planet is far from over. New discoveries continue to challenge our assumptions, forcing us to rethink our place in the cosmos. And as we continue to explore the universe, one thing is certain: the journey of discovery is just beginning. As we venture further into the cosmic wilderness, we encounter celestial objects that seem to defy categorization. These cosmic oddballs, neither quite planets nor easily classified as anything else, highlight the limitations of our current definition. Take for instance the superpuffs, gas giants with the mass of Earth but the diameter of Jupiter. These ethereal giants are so puffy, they'd practically float on water if you could find a cosmic bathtub big enough. They challenge our understanding of planetary density and formation, suggesting that there's still much we don't know about how planets come to be. Then there are the hot Neptunes, gas giants orbiting closer to their stars than Mercury does to our sun. These scorching worlds are constantly bombarded by intense radiation, creating exotic atmospheres and challenging our assumptions about where planets can exist. These cosmic outliers, along with a growing menagerie of other unusual objects, demonstrate that the universe is far more imaginative than our definitions might allow. It's like trying to classify all life on Earth based solely on the animals we see in our own backyards. In recent years, astronomers have turned their attention to the region beyond Neptune, a frigid realm known as the Kuiper Belt, where icy remnants from the solar system's birth still linger. This region is home to Pluto and a host of other dwarf planets, but some scientists believe it may also harbor a new class of planets altogether. These hypothetical planets, dubbed Planet 9 or Planet X, are thought to be several times the mass of Earth and could explain the peculiar orbital patterns of some Kuiper Belt objects. Their gravitational influence, though unseen directly, might be subtly sculpting the outer reaches of our solar system. If such planets do exist, they would challenge the IAU's definition in a fundamental way. Their distance from the Sun and the crowded nature of the Kuiper Belt would make it difficult for them to clear their orbits, despite their size and gravitational influence. The potential discovery of planets beyond Neptune highlights the need for a more flexible definition, one that recognizes the diverse environments and gravitational dynamics that shape planetary systems. The IAU's criterion of roundness, while seemingly straightforward, also merits further scrutiny. While it's true that gravity tends to mold objects with sufficient mass into spheres, the universe is full of surprises. For instance, rapidly rotating objects can become slightly flattened at their poles and bulge at their equators, giving them a slightly squashed appearance. This effect is particularly pronounced in objects with low densities or those located in systems with strong gravitational tides. Furthermore, collisions between celestial bodies can leave lasting scars, distorting their shapes and making it difficult to determine if they ever achieved hydrostatic equilibrium, the state of balance where gravity and internal pressure create a spherical shape. So, while roundness can be a useful indicator of planetary status, it's not a foolproof criterion. A planet's shape is merely one piece of the puzzle, and we must consider other factors, such as its composition and formation history, to get a complete picture. The IAU's emphasis on clearing one's orbital path, while intended to distinguish planets from asteroids and other debris, raises questions about the role of environment in planetary definition. A planet's ability to clear its neighborhood is not solely determined by its own mass and gravity, but also by the gravitational influence of its star and any nearby celestial bodies. A planet orbiting close to a massive star, for instance, might struggle to clear its path due to the star's overwhelming gravitational pull. Conversely, a planet in a sparsely populated region of space might easily achieve orbital dominance, even if it's relatively small. It's like comparing the cleaning efforts of someone living in a studio apartment to someone living in a sprawling mansion. The task is inherently more challenging in a more crowded environment. Therefore, a planet's ability to clear its orbit should not be viewed as a binary yes or no criterion, but rather as a spectrum of influence, taking into account the unique gravitational dynamics of its environment. As the limitations of the IAU's definition become increasingly apparent, some astronomers have proposed alternative frameworks for defining planets. These frameworks are designed to address the complexities and nuances that the current definition fails to capture. These new definitions aim to be more inclusive, encompassing the diversity of objects we're discovering, while still providing a clear distinction between planets and other celestial bodies. They seek to create a more comprehensive understanding that can adapt to new discoveries. One such proposal focuses on a planet's intrinsic properties, such as its mass, density, and composition, rather than its orbital characteristics. This approach allows for a more detailed and specific classification. This geophysical definition would recognize objects that have undergone planetary processes, such as internal differentiation, and the formation of a distinct core, regardless of their orbital environment. It emphasizes the physical and chemical processes that shape a planet. Another approach emphasizes the role of formation history, distinguishing between planets that formed from the protoplanetary disk around a star, and those that formed through other processes, such as the gravitational collapse of a gas cloud. This method highlights the diverse origins of planetary bodies. This definition acknowledges that planets can arise through multiple pathways and that their origin story is an essential part of their identity. It underscores the importance of understanding the history and evolution of each planet. These alternative definitions, while still under debate, reflect the evolving nature of our understanding of planets and the need for a more nuanced and inclusive classification system. They represent a step forward in our quest to comprehend the vast and varied universe we inhabit. The debate over what constitutes a planet is far from settled, and that's a good thing. Science thrives on questioning assumptions and refining our understanding of the universe as we gather more information. The IAU's definition, while imperfect, served a valuable purpose in sparking a global conversation about planets and their place in the cosmos. It forced us to confront our assumptions and grapple with the complexities of planetary formation and evolution. As we continue to explore the universe, discovering new and ever-stranger worlds, we must remain open to revising our definitions and embracing the unknown. The quest to understand planets is ultimately a quest to understand ourselves and our place in the grand tapestry of the cosmos. For centuries, we've clung to the idea that planets form around stars, like children gathering around a campfire. It's a comforting image, but what if it's not the whole story? Recent discoveries suggest that planetary formation might be a wilder, more chaotic process than we ever imagined. Enter the rogue planets, those cosmic nomads wandering the galaxy without a stellar home. These solitary wanderers, ejected from their birth systems by gravitational interactions, challenge our assumptions about planetary origins and hint at a universe teeming with unseen worlds. Imagine a vast cosmic pool table where young planetary systems collide and interact, scattering planets like billiard balls. Some are captured by other stars, while others are flung into the interstellar void, destined to wander the galaxy alone. These rogue planets, once thought to be rare anomalies, might be surprisingly common, perhaps outnumbering stars in our galaxy. Their existence suggests that planetary formation isn't always a neat and tidy process, and that planets can arise in the most unexpected of places. When considering what makes a planet, we often focus on its physical characteristics, its size, mass, and composition. These tangible attributes are easy to observe and measure, giving us a clear picture of the planet's physical nature. But what about its invisible properties, like its magnetic field? This unseen force can play a significant role in the planet's overall characteristics and behavior. Some scientists argue that a planet's magnetic field, often overlooked, might be a crucial factor in its evolution and even its habitability. This magnetic shield can influence everything from atmospheric retention to surface conditions. Earth's magnetic field, generated by the churning of molten iron in its core, acts as a protective shield, deflecting harmful radiation from the sun and preserving our atmosphere. This dynamic process is essential for maintaining the conditions necessary for life. Without it, our planet would be a barren wasteland, stripped of its life-giving air and water. The absence of a magnetic field could lead to the erosion of the atmosphere, leaving the surface exposed to the harsh environment of space. Could a magnetic field be a prerequisite for life as we know it? This question challenges our understanding of what makes a planet habitable. It's a question that has profound implications for our search for extraterrestrial life. If magnetic fields are essential for habitability, it could narrow down the list of potential life-supporting planets. If a planet lacks a substantial magnetic field, it might be vulnerable to the harsh realities of space, making it an unlikely candidate for hosting life. The solar wind and cosmic radiation could strip away its atmosphere, rendering it inhospitable. The presence of a magnetic field, while not explicitly included in the IAU's definition, might be an essential criterion for habitability and a key factor in distinguishing planets from lifeless rocks. This invisible shield could be the difference between a thriving world and a desolate one. In our quest to find another Earth, we've become obsessed with water, and for good reason. Water is essential for life as we know it, and its presence on other worlds would be an encouraging clue in our search for extraterrestrial life. Recent discoveries suggest that water might be surprisingly common in the universe. From icy moons in our own solar system to distant exoplanets with atmospheres rich in water vapor, the evidence is mounting that water is not unique to Earth. Imagine a planet covered entirely in a vast global ocean, its depths teeming with strange and wonderful life forms. These ocean worlds, once relegated to the realm of science fiction, might be a common type of planet in the universe. The presence of liquid water, while not a guarantee of life, would dramatically increase a planet's habitability potential and make it a prime target for further exploration. It might even lead us to reconsider our definition of a planet, placing greater emphasis on the potential for life than on arbitrary size or orbital characteristics. As we discover more and more exoplanets, the question arises, what makes a planet truly special? Is it simply its size, its composition, or its orbital dance around a star? Or could it be something more profound, something that speaks to the very essence of life itself? Some scientists propose that we move beyond purely physical characteristics and consider a planet's potential for life as a key factor in its definition. This habitability index would take into account various factors, such as a planet's temperature, the presence of liquid water, and the composition of its atmosphere. Imagine a cosmic ranking system where planets are judged not just on their size or mass, but on their ability to support life. This new perspective would shift our focus from simply cataloging celestial objects to identifying those with the greatest potential for harboring life beyond Earth. While a habitability index is still a theoretical concept, it highlights the growing recognition that life might be a defining characteristic of planets, and that our search for extraterrestrial life is inextricably linked to our understanding of what makes a planet truly special. The ongoing debate over planetary definitions has implications not just for distant exoplanets, but also for our understanding of our own cosmic neighborhood. If we adopt a more nuanced and inclusive definition, how might it change our view of the solar system we call home? Could some of the objects currently classified as dwarf planets, such as Pluto, Eris, or Makemake, be elevated to full planetary status? What about the larger moons in our solar system, some of which are larger than Mercury? Could they be considered planets in their own right? And what about the countless smaller bodies, the asteroids, comets, and icy remnants that litter the space between planets? While they might not meet the traditional criteria for planethood, They play important roles in the solar system's history and evolution. Redefining planets would not diminish the significance of these objects but rather acknowledge their diversity and complexity, highlighting the rich tapestry of worlds that make up our cosmic neighborhood. The search for a definitive answer to the question, what is a planet, is ultimately a journey of exploration, a quest to understand the universe and our place within it. As we continue to peer deeper into the cosmos, discovering new and ever-stranger worlds, we must be prepared to challenge our assumptions and embrace the unknown. The universe is full of surprises, and our definitions should reflect this inherent complexity. Rather than clinging to rigid categories, we should strive to develop a more fluid and inclusive understanding of planets, one that acknowledges their diversity and celebrates the sheer wonder of their existence. The journey of discovery is just beginning, and the future of planetary science is filled with possibilities. By embracing the unknown and challenging our preconceived notions, we open ourselves up to a universe of wonder and expand our understanding of the cosmos and our place within it. As we've journeyed through the cosmos of planetary science, one thing has become abundantly clear. Defining a planet is not as simple as it seems. What was once a straightforward concept has evolved into a complex and fascinating debate, fueled by new discoveries and a deeper understanding of the universe. The International Astronomical Union's 2006 definition, while providing a useful framework, has faced increasing scrutiny as we uncover the sheer diversity of celestial objects that populate our universe. Rogue planets, superpuffs, ocean worlds. These cosmic oddballs challenge our assumptions and push the boundaries of what we thought we knew about planets. This ongoing debate highlights the dynamic nature of science itself. It's not about clinging to rigid definitions, but about embracing new evidence, questioning our assumptions, and constantly refining our understanding of the natural world. The definition of a planet is not a static concept but an evolving one, shaped by our ongoing exploration of the cosmos. The quest to define a planet is not merely an academic exercise. It has profound implications for our understanding of the universe and our place within it. As we launch increasingly powerful telescopes and explore the cosmos in greater detail, the way we define planets will shape our priorities and guide our search for life beyond Earth. Will we focus our efforts on finding planets that fit neatly into our existing definitions? Or will we broaden our horizons, embracing a more inclusive view of planethood that encompasses the full spectrum of planetary diversity? The choices we make today will determine the course of planetary science for generations to come. Imagine a future where we discover a planet that challenges our very notion of what life is or where it can exist. Will our definitions be flexible enough to accommodate such a discovery? Or will we risk overlooking a truly profound finding because it doesn't fit within our preconceived notions? Now that we've explored the ever-evolving world of planetary definitions, we want to hear from you. What do you think constitutes a planet? Should we stick with the current definition, or is it time for a change? Share your thoughts and theories in the comments below. Do you think a planet's ability to clear its orbit is essential? Or should we focus on other factors like its composition or potential for life? Let's keep the conversation going and explore the possibilities together. Thank you for joining us on this incredible adventure through the ever-evolving world of planetary science. We hope you found it as mind-boggling and awe-inspiring as we did. If you enjoyed this cosmic journey, please give this video a thumbs up and subscribe to our channel for more explorations of the universe and its many wonders. And as always, keep looking up, keep questioning, and never stop exploring the universe around you. Until next time, keep those curiosity thrusters firing.